So in this video, we are going to talk about the non-inverting OpAmp configuration, and we will see how to use this OpAmp as a voltage follower. Now in the last video, we had seen the inverting OpAmp configuration, and in that configuration, we had seen that using the negative feedback, we can control the gain of this OpAmp. And in that configuration, we have applied the input to this inverting terminal of the OpAmp, and we have grounded the non-inverting terminal. Now let us see what happens when we apply this input to this non-inverting terminal. So let's say we have applied the input to this non-inverting terminal and we have grounded this inverting terminal. So this kind of configuration is known as the non-inverting OpAmp configuration, because here the output and input are in a phase. So now for this configuration, let us find the relation between this output and the input voltage. So now before we find the relationship between the output and input voltage, let me redraw the same circuit so that you can have a better idea about the circuit. So here I have redrawn the same circuit in a different way. So here we have applied the input to this non-inverting input terminal, and we have a feedback resistance RF between the output and the inverting input terminal. And if you see here, the one end of this resistance R1 is connected to the resistance RF, and another end of this resistor R1 is connected to the ground. So if you see here, the fraction of output voltage is going as a feedback to this inverting input terminal. So let us say here at this point the voltage is Vx, and this Vx voltage is going as a feedback to this inverting input terminal. Now using the voltage divider rule, we can say that this voltage Vx, that is equal to R1 divided by R1 plus Rf into Vout. So this voltage will be going as a feedback to this inverting input terminal. So at this point also the voltage will be equal to Vx. Now in the last video we had seen that whenever we are using this OpAmp in a negative feedback configuration, then there will be a virtual short between both the input terminals of this OpAmp. It means that whatever voltage that appears at one end of this input terminal, the same voltage will appear at the another end of the input terminal. It means that V plus, that is equal to V minus, and that is because of this virtual short between this non-inverting and the inverting input terminal. So here in this configuration, we are applying the input voltage to this non-inverting terminal. That means V plus, that is equal to V in. So because of this virtual short at this inverting input terminal also, the voltage should be equal to V in. That means V minus should be equal to V in. And we know that V minus, that is equal to Vx. So we can write this input voltage V in, that is equal to R1 divided by R1 plus Rf into Vout. Or we can say that Vout divided by V in, that is equal to R1 plus Rf divided by R1, that is equal to 1 plus Rf divided by R1. So this will be the closed loop gain of this non-inverting OpAmp configuration. So in non-inverting OpAmp configuration, the relation between the output and input is equal to 1 plus Rf divided by R1. So in this non-inverting OpAmp configuration also, just by controlling the value of this Rf and R1, we can control the gain of this OpAmp. But in this non-inverting OpAmp configuration, the output and input will have a same phase. So let's say if I apply 1 volt of DC signal at this non-inverting input terminal, and if I take value of R1 as 1 kilo ohm, then my gain of this OpAmp will be equal to 1 plus 2 divided by 1, that is equal to 3. So at the output, I will get 3 volt of DC signal. Or instead of DC voltage, let's say if I apply a 1 volt of sinusoidal signal, and if I have a value of Rf as 2 kilo ohm and R1 as 1 kilo ohm, then at the output, I will get a 3 volt of amplified AC signal, which is having a same phase with respect to input signal. So in this non-inverting OpAmp configuration, just by controlling the value of this feedback resistance Rf and R1, we can control the gain of this OpAmp, and in this configuration, the output and input are in a phase. So this is all about the non-inverting OpAmp configuration. So now here the question is, what is the advantage of this non-inverting OpAmp configuration over this inverting OpAmp configuration? Because if you see both the configurations, in both the configurations, we can control the gain using this feedback resistance Rf and R1. So let us find out some of the advantages of non-inverting OpAmp configuration over this inverting OpAmp configuration. Now, one of the obvious advantage of this non-inverting op-amp configuration is that the output and input both are in a phase. While in case of this inverting op-amp configuration, there is a 180-degree phase shift between the output and the input voltage. Apart from this, if you see this non-inverting op-amp configuration, then in this configuration, the input impedance of the circuit is very high. And if we consider the ideal op-amp, then in that case, the input impedance of the circuit is infinite. While in case of this inverting op-amp configuration, the input impedance depends upon the value of R1. So if we consider the ideal op-amp, then in that case, the input impedance of this inverting op-amp will be equal to R1. So now let us derive the expression for this input impedance in case of this inverting as well as the non-inverting op-amp configuration. So now if you see the inverting op-amp configuration, then in this configuration, the input impedance is the impedance that is seen through this voltage source Vin. Or in another words, we can say that the input impedance of this configuration is equal to the input voltage divided by the current that is going into the circuit. So let us say the current I in is going into this circuit. So now here the ratio of input voltage divided by this input current will give us the input impedance of this configuration. Now we know that in this inverting op-amp configuration, this node will act as a virtual ground because here this non-inverting terminal is already grounded. So we can say that this I in that is equal to V in divided by R1, or we can say that R1 that is equal to V in divided by I in. Now we know that V in divided by I in is equal to input impedance. So we can say that the input impedance of this inverting op-amp configuration is equal to R1. So the input impedance of this configuration depends upon the value of R1. So let's say if value of R1 is very low, then in that case the input impedance of the circuit will be low. So similarly, let us find the input impedance of this non-inverting op-amp configuration. So in this non-inverting op-amp configuration also, the input impedance is the impedance that is seen through this voltage source Vin. So let us once again assume that current that is being supplied by this voltage source is In, and the ratio of this Vin divided by In will gives us the input impedance of this non-inverting op-amp configuration. So now if we consider this op-amp as ideal op-amp, then there will not be any current that is going into this inverting and the non-inverting terminals, or we can say that this input current In that is equal to approximately 0, and hence we can say that the input impedance is equal to infinite. So now in any circuit, whenever we have a very high input impedance, then that will ensure that the source that is connected to that circuit will not be get loaded. So let us understand this point. So let us say we have one voltage source Vs and it is having a source resistance Rs, and it is connected to one circuit, and this circuit has an input impedance Zin. So now whenever the value of this input impedance is comparable to the value of this Rs, then in that case the voltage that appears across the two terminals of the circuit will be equal to Zin divided by Zin plus Rs into Vs. And as Zin is equal to Rs, then the value of voltage V will be equal to Vs by 2. So only half of the voltage will appear across this circuit. So in any circuit, the value of input impedance should be very high, so that whatever voltage that is being applied to that circuit will entirely appear across that circuit. So in this case of non-inverting op-amp configuration, as the input impedance is approximately equal to infinite, or in practical case it is very high, so whatever voltage that is applied to that circuit will entirely appear across that circuit. So that is the advantage of this non-inverting op-amp configuration. In this non-inverting op-amp configuration, let us say we have Rf that is equal to 0 and R1 that is equal to infinity. Then the circuit will look like this. So this circuit is known as the op-amp as a voltage follower circuit, or op-amp as a buffer. So here we have shorted this output terminal with this inverting op-amp terminal. So at this point voltage will be equal to V out, and because of the feedback V minus that is equal to V plus, or we can say that because of the feedback we have a virtual short between this inverting and the non-inverting op-amp terminals. So we can say that V minus will be equal to V in, or we can say that V in will be equal to V out. So it means that whatever voltage that is applied to this non-inverting op-amp terminal, the same voltage will appear at the output of this op-amp. So we can say that the output voltage follows the input voltage, and that is why this circuit is known as the voltage follower circuit. So the characteristic of this circuit is that the input impedance of this circuit is very high, or ideally it is infinite, and the output voltage will be equal to input voltage. So because of these two characteristics, this circuit is also known as the buffer circuit, because it will pass whatever input that is coming to it as it is, and it will provide the very high input impedance. So using this buffer circuit, we can isolate the two different circuits, and at the same time we can ensure that whatever voltage that is appearing at the output of the one circuit will appear at the input of the another circuit. And that is particularly useful when we have a low input impedance in one circuit. So I hope in this video you understood the non-inverting op-amp configuration and the advantages of this non-inverting op-amp configuration over the inverting op-amp configuration, and how to design the voltage follower or the buffer circuit using this op-amp.